The proposed RIME algorithm enhances robust parameter extraction for photovoltaic models by improving exploration and exploitation. To promote population diversity, a differential evolution mutation operator is integrated, while a novel exploitation strategy combines randomization and neighborhood approaches. This improved approach is applied to estimate optimal parameters for single-diode, double-diode, and triple-diode models across various PV cell and module types. Statistical analysis of 100 runs demonstrates the accuracy and robustness of the TEIMRE algorithm in parameter estimation for different PV models under varying environmental conditions. The significance of reliable PV models for planning, optimization, and control of PV systems is underscored, highlighting the challenges in obtaining robust solutions with traditional methods. By integrating the differential evolution mutation operator, the algorithm enhances population diversity, ensuring a more comprehensive search space. The novel exploitation strategy combines the benefits of randomization and neighborhood approaches, striking a balance between exploration and exploitation. The TEIMRE algorithm's robust performance is attributed to its ability to adapt to varying environmental conditions, ensuring accurate parameter estimations for diverse PV models. This research contributes to the development of reliable PV models, crucial for the effective planning, optimization, and control of PV systems. Accurate parameter identification is crucial for photovoltaic PV models, particularly in varying environmental conditions. However, existing models, such as the single-diode, double-diode, and triple-diode models, rely on parameters not always provided in manufacturers' datasheets, limiting their accuracy. To address this challenge, robust methods are needed to estimate these parameters. Three categories of methods exist: analytical, numerical, and meta-heuristic. The latter has garnered attention, with the RIME algorithm showing promising results. However, it is prone to getting trapped in local optimums, highlighting the need for further development. PV parameter identification is a complex task, and the limitations of current methods underscore the need for more robust algorithms. The development of such algorithms would enable more accurate PV modeling, facilitating the optimization of PV systems under varying environmental conditions. Further research is necessary to overcome the challenges in PV parameter identification, including the development of algorithms that can efficiently and accurately estimate model parameters. This would have significant implications for the improvement of PV system performance and the integration of PV systems into the grid. The current limitations of the RIME algorithm, particularly in its exploitation phase, are discussed. Enhancements focusing solely on either exploration or exploitation have not fully addressed the issue. The SCLRIME and IDRM variants are highlighted as examples of such limitations. The classic RIME algorithm's update strategy in the exploitation phase is identified as a key issue, where agents may become trapped in local optima. In contrast, the TERIME algorithm proposed aims to enhance both exploration and exploitation capabilities simultaneously. This includes incorporating a demutation operator for enhanced exploration and a neighborhood strategy for more focused exploitation. The effectiveness of TERIME is demonstrated through comparative results on 3 PV models and datasets. The development of a novel optimization algorithm, TERIME, is presented as an enhanced version of the randomized initial middle-end RIME algorithm. The primary objective is to improve the efficiency of photovoltaic PV model parameter estimation. Two widely used PV models, the single-diode model (SDM) and double-diode model (DDM), are introduced, and the optimization problem is formulated. TERIME is a robust meta-heuristic algorithm designed to overcome the limitations of existing methods. Its superior performance is attributed to the incorporation of a novel initialization strategy, adaptive exploration-exploitation, and a dynamic adjustment mechanism. This results in enhanced convergence rates and improved solution quality. Experimental results demonstrate the effectiveness of TERIME in estimating PV model parameters, outperforming several state-of-the-art meta-heuristic algorithms. The algorithm's robustness is evaluated using statistical metrics, including mean absolute error, mean squared error, and coefficient of determination. The results show that TERIME achieves significant improvements in estimation accuracy and computational efficiency, making it a promising approach for PV model parameter estimation. Future work directions include extending TERIME to accommodate complex PV systems and integrating it with other optimization techniques to further enhance its performance. The paper discusses the development of photovoltaic (PV) models for accurately describing the current voltage (IV) characteristics of solar cells. It presents 3 models: the single-diode model, SDM, double-diode model, DDM, and triple-diode model, TDM. The SDM is the simplest, considering only one diode, while the DDM and TDM account for additional diodes to better represent recombination losses. The TDM, being the most complex, includes 3 diodes and is capable of modeling recombination losses in defect regions and grain sites. The paper also formulates an optimization problem to extract the parameters of these models by minimizing the root mean square error, RMSE, between the calculated and measured IV curves. This approach aims to make the constructed IV curve consistent with the measured one. Mathematical modeling of photovoltaic cells is crucial for accurate performance prediction and optimization. This study employs the single-diode model, SDM, double-diode model, DDM, and triple-diode model, TDM, to simulate photovoltaic behavior. The Lambert-W function is utilized for its superior accuracy and efficiency in calculating current. In the SDM, the equation is rewritten as a function of the Lambert-W function, a multibranched function defined by W, x, e caret W, x, equals x for any complex number x. This yields an expression for the calculated current in terms of photonic and thermal current components, series resistance, and other parameters. The DDM extends the SDM by incorporating 2 photonic and 2 thermal current components, along with 2 series resistances. The TDM further expands this by introducing 3 photonic and 3 thermal current components, along with 3 series resistances. Notably, a photovoltaic module comprising multiple cells connected in series can be expressed by these equations, with the thermal current equation modified to account for the number of cells connected in series. To optimize the parameters of these photovoltaic models, the authors introduce the RIME algorithm, a physics-based meta-heuristic optimization technique inspired by the natural process of RIME formation. The optimization procedure initiates with the initialization of the RIME population, where n RIME agents are randomly positioned within the search space to form the initial population. The RIME algorithm, inspired by the formation of RIME ice, introduces 2 key strategies: soft RIME search and hard RIME puncture mechanism. Soft RIME search, modeled after the slow and random development of soft RIME under breezy conditions, efficiently spans the entire search space and avoids local optima. The location of each particle is formulated using equation 20, which involves parameters such as control parameter R1, random number R2, adjustment factor theta, environmental condition effect beta, and condensation probability factor E. These parameters are calculated using equations 21 to 23, where T max represents the maximum number of iterations, T indicates the present iteration number, W is assigned as 5, and represents the rounding operator. The hard RIME puncture mechanism, inspired by the simpler and more regular growth pattern of hard RIME under strong gale conditions, enhances convergence and avoids local optima. Mathematically, it is expressed as equation 24, where norm, if x represents the normalized fitness value of the ith search agent with respect to all agents, determining the selection probability of the specific agent, and R3 is a random number ranging between 0 and 1. The TERIME algorithm builds upon the RIME algorithm, enhancing both exploration and exploitation phases to tackle complex optimization problems more effectively. A positive greedy selection mechanism ensures the updated search agent's fitness value improves incrementally, comparing it to the previous agent. To introduce diversity and avoid local optima, the enhanced exploration approach incorporates the rand1 operator, which modifies the original exploration phase equation with a random mutation factor. This strategy helps the algorithm escape local optima. The exploitation strategy combines 2 approaches: crossover and Gaussian exploitation. The crossover strategy utilizes a randomization exploitation strategy, where a crossover factor, derived from an equation, decreases as the iteration number increases. This crossover factor promotes a more diverse solution space. The Gaussian exploitation strategy, a neighborhood exploitation strategy, enables a focused search around the current best solution, preventing entrapment in local optima and improving convergence towards the global optimum. By integrating these strategies, the TERIME algorithm demonstrates improved performance in solving complex optimization problems. In the RIME algorithm, a novel expression for the exploitation phase is derived. The standard deviation sigma is set to 0.001 for a specific problem. The original exploitation phase is rewritten using a normally distributed random number with a mean of j best x and a standard deviation of j best x sigma. This new expression combines crossover and Gaussian exploitation strategies, enhancing the algorithm's ability to avoid local optima and improve convergence speed. The application procedure of TERIME is also discussed, highlighting the need to adjust agent positions to prevent early convergence issues near the search area boundaries. This is achieved through the strategy expressed in equation 31, which involves adding a random component to the new position. This refined approach improves the algorithm's efficiency and accuracy in solving complex optimization problems. The proposed TERIME algorithm is applied to 3 different photovoltaic (PV) systems in this section of the research paper. The datasets used are widely recognized in the literature for assessing parameter estimation techniques for PV models. The first dataset, a commercial solar cell from RTC France, has a diameter of 57 mm with IV data recorded at 33 degrees Celsius under full illumination. The flowchart of the TERIME algorithm, provided in Figure 2, illustrates the process of parameter estimation for the PV models. This algorithm aims to improve the accuracy and efficiency of parameter estimation, which is crucial for optimizing the performance of PV systems. The validation schemes employed in this study are designed to evaluate the effectiveness of the TERIME algorithm in estimating the parameters of the PV models accurately. By using these datasets, the researchers can compare the performance of the proposed algorithm with existing methods and assess its potential for real-world applications. In conclusion, this section provides a comprehensive overview of the experimental setup and the datasets used to validate the TERIME algorithm. It highlights the significance of this research in enhancing the efficiency of PV systems and underscores the importance of accurate parameter estimation techniques for optimizing solar cell performance. The novel TERIME algorithm is proposed for parameter extraction of photovoltaic (PV) models, and its performance is compared to various state-of-the-art algorithms for PV parameter estimation, including RIME variants and other prominent methods. The robustness of these algorithms is evaluated through their root mean square error (RMSE) values in extracting parameters for 3 distinct PV systems: a monocrystalline PV cell, RTC France, a polycrystalline PV module, Watt-PWP 201, and a polycrystalline S75 PV module. Experimental IV characteristics of these PV systems were measured under diverse environmental conditions. Table 1 presents the variation range of parameters in the single-diode model, SDM, double-diode model, DDM, and triple-diode model, TDM, for the 3 PV systems. To validate TERIME's effectiveness, 6 competing algorithms are employed and compared: MRIME, SLCRIME, SRIME, DO, NGO, and CL-RAO1. Each algorithm is run 100 times on each PV model to account for random results. Maximum, mean, minimum, and standard deviation RMSE values are calculated to assess the performance and robustness of these algorithms. The results indicate that for the SDM, TERIME, MRIME, and CL-RAO1 consistently achieve a robust global optimum in all 100 runs. Notably, for the DDM, TERIME outperforms other algorithms, delivering the best results for mean, maximum, and standard deviation values. These findings demonstrate TERIME's superior performance and robustness in extracting PV model parameters. A comparison of root mean squared error, RMSE, results from 100 runs for the single-diode model, SDM, double-diode model, DDM, and 3-diode model, TDM. Parameter extraction of RTC France is presented in Table 2. The results show that for the SDM, all algorithms exhibit similar performance, with TERIME, MRIME, SLCRIME, and CL-RAO1 achieving the best min, mean, and max values. However, for the DDM, TERIME outperforms other techniques, achieving the best mean and max values. Regarding the TDM, MRIME gives the best min value, followed by TERIME, but TERIME achieves the best mean and max values. The table provides a detailed comparison of the RMSE results, including the standard deviation, for each algorithm and PV model. The results indicate that TERIME is markedly superior to other techniques, especially for the DDM, while MRIME and CL-RAO1 exhibit inferior robustness when the complexity of the PV model increases. Figure 3 illustrates the error box plots for the three excellent algorithms, TERIME, MRIME, and CL-RAO1, demonstrating that TERIME exhibits robust results with good performance for all PV models, particularly for the DDM. In contrast, MRIME and CL-RAO1 present inferior results when the complexity of the PV model increases, highlighting the importance of considering model complexity when selecting a parameter extraction algorithm. Error box plots and average convergence of three algorithms for parameter extraction, namely SDM, DDM, and TDM, are presented. Figure 3 displays error box plots, illustrating the performance of these algorithms. Average convergence, as shown in Figure 4, reveals that TERIME exhibits the fastest initial convergence for SDM, while MRIME outperforms initially for DDM and TDM. However, TERIME surpasses all other algorithms after a certain number of iterations, underscoring its significance. This highlights the importance of TERIME, MRIME, and CL-RAO1 in achieving better performance compared to other algorithms, which often get trapped in local optima or converge slowly. The convergence performance of three algorithms, namely SDM, DDM, and TDM, is evaluated for parameter extraction in RTC France, with a focus on the competitive performance and robustness of the TERIME algorithm. In a comprehensive analysis of 100 runs, Figure 4 reveals that TERIME consistently outperforms its counterparts in terms of mean and maximum values, despite exhibiting a slightly inferior minimum value compared to MRIME in TDM parameter extraction. This superior performance is further visualized in Figure 5, where a lower ranking indicates better performance, solidifying TERIME's position as a competitive algorithm with satisfactory performance and excellent robustness in this context. The paper delves into the efficacy of the proposed parameter extraction algorithm, TERIME, for photovoltaic models. A comparative analysis of three prominent algorithms SDM, DDM, and TDM is presented in Fig. 5, showcasing their performance in replicating the IV characteristics of solar cells for RTC France. To further assess the precision of these models, the individual absolute error, IAE, for the output current is calculated using EQ. 32. The IAEs of SDM, DDM, and TDM for the RTC France obtained by the TERIME are illustrated in Fig. 6, demonstrating that the IAE for all measured data does not exceed 1.6 times 10 to the 3, with TDM having the smallest IAE overall, followed by DDM and then SDM. This suggests that increasing the number of diodes can enhance modeling accuracy in this context. Furthermore, the calculated IV curves from the SDM, DDM, and TDM using TERIME are compared with the measured one in Fig. 7, indicating that the optimal parameters obtained by TERIME accurately represent the IV characteristics of the solar cells, thereby demonstrating the effectiveness of the proposed method. This is crucial for the development of efficient solar cells and their integration into solar power systems. The accuracy of cell parameters estimated by TERIME is demonstrated through a close fit between calculated IV curves and measured data, as shown in Figure 7 for the RTC France PV module. For the PWP 201 PV module, a comparison of root mean squared error, RMSE, values for parameter extraction using single-diode, double-diode, and three-diode models with different algorithms is presented in Table 3. Notably, TERIME consistently yields robust globally optimal values across all 100 runs for all PV models, with RMSE values of 1.980210 times 10 to the 3, 1.235854 times 10 to the 3, and 1.235854 times 10 to the 3, respectively. In contrast, while MRIME and CL-RAO1 demonstrate robust performance for the single-diode model, their performance degrades as the complexity of the PV model increases. The supplementary material provides the PV parameters corresponding to the smallest RMSE for different algorithms. The table highlights the superior performance of TERIME in terms of consistency and accuracy, with standard deviations on the order of 1.3 times 10 to the 17 for all PV models, indicating a high degree of robustness. In the realm of photovoltaic PV model parameter extraction, the performance of various algorithms is crucial. This study compares the root mean squared error, RMSE, of MRIME, CL-RAO1, and TERIME algorithms for the SDM, DDM, and TDM models. The results show that TERIME outperforms MRIME and CL-RAO1, exhibiting fewer outliers and improved robustness. A critical aspect of these algorithms is their convergence speed to the global optimum. The average convergence of the three algorithms is illustrated, with TERIME demonstrating the fastest convergence speed for the SDM model. This is supported by Figure 8, which presents error box plots, and Figure 9, which displays the average convergence. The superior performance of TERIME is attributed to its ability to effectively handle the complexities of PV model parameter extraction. The results suggest that TERIME is a more reliable and efficient algorithm for this task, making it a promising tool for researchers and engineers in the field. In the context of parameter extraction for photonic waveguide platforms, the comparative convergence performance of various optimization algorithms is discussed. For the DDM, MRIME exhibits the quickest convergence within the first 20,000 iterations, while TERIME outperforms all other algorithms after approximately 40,000 iterations. In the TDM, MRIME has the fastest convergence before 80,000 iterations, followed by CL-RAO1, but TERIME overtakes MRIME after 80,000 iterations. The results indicate that RIME and SRIME are easily trapped in local optima, whereas DO, NGO, and SLCRIME converge slowly and fail to reach the vicinity of global optima for the DDM and SDM. Figure 9 visually represents the average convergence performance from 100 runs for parameter extraction of PWP 201 across different models. These findings underscore the importance of selecting an appropriate optimization algorithm based on the specific model and the desired convergence rate. The choice of algorithm can significantly impact the efficiency and accuracy of parameter extraction in photonic waveguide platforms. The comparative analysis on the 19th page of the research paper evaluates the performance of three algorithms TERIME, MRIME, and CL-RAO1 in extracting parameters for photovoltaic PV cells using the double-diode model, DDM, and triple-diode model, TDM. The primary objective is to assess their ability to identify parameters of a specific PV cell, PWP 201. Figure 10 illustrates the ranking of these algorithms based on their performance metrics, such as minimum, mean, and maximum errors. It is evident that TERIME consistently outperforms the other two algorithms in terms of parameter extraction accuracy for both DDM and TDM. Figure 11 demonstrates the goodness of fit between the calculated data and measured data for PWP 201, with all measured data below 4E3, regardless of the PV model type. This indicates the effectiveness of TERIME in accurately modeling the PV cell's behavior. Finally, Figure 12 compares the calculated IV curves from the single-diode model, SDM, DDM, and TDM using parameters extracted by TERIME with the actual measured IV curve. The close alignment of the calculated curves with the measurements suggests that the optimal parameters estimated by TERIME are very close to the actual cell parameters. Overall, this page highlights the superior performance of TERIME for parameter extraction in PV cells, emphasizing its potential in enhancing the accuracy of solar panel simulations and efficiency assessments. The IV curve measurements of the PWP 201 solar panel are compared with those calculated using the single-diode model, SDM, double-diode model, DDM, and triple-diode model, TDM. This comparison highlights the performance differences between meta-heuristic algorithms, particularly in parameter extraction for DDM and TDM. To further analyze this, root mean square error, RMSE, results for parameter extraction on DDM and TDM under varying irradiance and temperature are presented. The focus is on MRIME and CLRAO1, which consistently demonstrate outstanding performance. Data from Table 4 and error box plots in Fig. 13 show TERIME's supremacy in terms of mean, max, and STD, with fewer outliers compared to other algorithms. This underscores TERIME's robustness under diverse conditions. The table presents the results of direct digital modulation, DDM, parameter extraction using three algorithms, TERIME, MRIME, and CLRAO1, under various irradiance and temperature conditions. The mean, median, and standard deviation of the root mean squared error, RMSE, are displayed for each algorithm, along with the p-value indicating the statistical significance of the results. Under an irradiance of 800 W per square meter and a temperature of 25 degrees Celsius, TERIME and MRIME exhibit similar performance, while CLRAO1 achieves a slightly better RMSE. When the irradiance increases to 1000 W per square meter and temperatures range from 20 degrees Celsius to 60 degrees Celsius, CLRAO1 consistently outperforms the other two algorithms, with MRIME performing better than TERIME in most cases. Error box plots in Figure 13 provide a visual representation of the spread of RMSE values under these conditions. The plots illustrate that CLRAO1 tends to have a lower median RMSE and a smaller interquartile range compared to the other two algorithms. Subsequent plots compare the RMSE values of the three algorithms under different irradiance and temperature conditions, with CLRAO1 consistently demonstrating better performance. The iteration number is plotted on the z-axis, and the RMSE values are plotted on the y-axis. The plots show that CLRAO1 achieves a lower RMSE value than TERIME and MRIME in most scenarios, indicating its superior performance in DDM parameter extraction. The performance of various algorithms for time-domain multipath (TDM) parameter extraction is evaluated under different irradiance and temperature conditions. A comparative analysis of the root mean square error (RMSE) results of TERIME, MRIME, and CLRAO1 algorithms reveals that TERIME consistently outperforms its counterparts, demonstrating its robustness across varying environmental conditions. As depicted in Table 5 and visualized in Fig. 14, TERIME exhibits the lowest RMSE and the fewest outliers across all conditions, underscoring its effectiveness in extracting TDM parameters. This superior performance is attributed to TERIME's ability to adapt to changing irradiance and temperature conditions, ensuring accurate parameter extraction. Notably, the results highlight TERIME's resilience in the presence of outliers, which is critical in real-world applications where data quality can be compromised. The comparative analysis provides valuable insights into the strengths and limitations of each algorithm, informing the selection of optimal algorithms for TDM parameter extraction in various environmental scenarios. The findings of this study have significant implications for the development of robust and accurate TDM parameter extraction methods, particularly in applications where environmental conditions are dynamic and unpredictable. The comparative analysis of three algorithms for parameter extraction in photovoltaic cells, focusing on the S75 model under varying irradiance and temperature conditions, demonstrates the superiority of TERIME. Error box plots in Fig. 14 illustrate TERIME's consistent outperformance over MRIME and CL-RAW1 for TDM parameter extraction. Fig. 15 shows the average ranking of these algorithms for both DDM and TDM, with TERIME ranking highest in mean and max for both, although MRIME surpasses it in min for TDM. The table at the bottom of the page provides numerical comparisons, further supporting TERIME's effectiveness in offering the lowest error rates across all metrics. The TERIME algorithm, an improved version of RIME, addresses the robustness challenge of photovoltaic (PV) parameter extraction by integrating the rand1 mutation operator for population diversity and randomization and neighborhood strategies for exploitation. It also introduces a crossover strategy for information exchange and a Gaussian exploitation strategy. Compared to other state-of-the-art methods on 3 PV datasets, TERIME consistently finds robust results, outperforming others, especially with increasing PV model complexity. For instance, on the RTC France and PWP 201 datasets, TERIME improves the average root mean squared error (RMSE) values by 3.24% and 2.57% for DDM, and 1.70% and 0.34% for TDM, respectively. TERIME demonstrates robust solutions under varying environmental conditions, achieving the best average rankings for mean and max values in DDM and TDM parameter extraction. Although it may not have the fastest convergence speed initially, its consistent rapid descent speed throughout iterations ensures robust results. The proposed TERIME algorithm serves as a reliable optimization tool for accurate PV parameter identification under varying conditions, and its exploitation strategy can inspire improvements in other meta-heuristic algorithms. The modeling of photovoltaic systems, particularly the short-circuit current under standard test conditions, is a crucial aspect of photovoltaic analysis. This involves an equation, EQ 33, which relates the short-circuit current to irradiance and temperature. The parameters used in this equation are extracted from the datasheet of the S75 solar panel. Accurate modeling and analysis of photovoltaic systems rely heavily on understanding these parameters. Parameter extraction methods for photovoltaic models have been extensively reviewed, citing 24 research papers published between 2013 and 2024. These papers focus on estimating parameters of single-diode, double-diode, and 3-diode photovoltaic models, as well as more complex models with 5 and 7 parameters. Optimization algorithms employed include arithmetic optimization, modified third-order Newton-Raphson methods, hybrid adaptive Nelder-Mead simplex algorithm, bio-inspired meta-heuristic frameworks, and physics-based optimization methods. These algorithms are used to extract parameters from manufacturers' datasheets, experimental data, and numerical calculations. Accurate parameter estimation is crucial for predicting the performance of solar cells and modules under varying operating conditions. The reviewed papers demonstrate the effectiveness of various optimization algorithms in extracting parameters, such as the ideality factor, series resistance, shunt resistance, and photocurrent, among others. Some papers provide in-depth analyses of single-diode model parameters, while others focus on identifying unknown parameters of solar cell models using comprehensive overviews of available approaches. The application of meta-heuristic algorithms for parameter extraction of solar photovoltaic cell and module models is also reviewed. This literature review provides a comprehensive overview of the state-of-the-art in parameter extraction methods for photovoltaic models, highlighting the diversity of approaches and optimization algorithms used in this field. In the realm of advanced research, the compilation of comprehensive lists is often a pivotal step in understanding and organizing complex data. This page serves as a repository for such lists, providing researchers with an essential tool for navigating and interpreting intricate datasets. These lists encompass a wide range of topics, from mathematical algorithms to biological pathways, and are designed to facilitate the exchange of information among experts in various fields. By consolidating this data into easily accessible formats, researchers can quickly identify patterns, trends, and correlations that might otherwise remain hidden within the vast expanse of raw data. Each list included on this page has been meticulously curated to ensure accuracy and relevance, reflecting the latest findings and methodologies in their respective disciplines. This not only aids in the validation of existing research but also fosters innovation by providing a solid foundation upon which new investigations can be built. Furthermore, these lists are not static entities. They are continually updated to reflect emerging trends and discoveries, ensuring that they remain a vital resource for the research community. As such, they serve as a testament to the dynamic nature of scientific inquiry, where knowledge is constantly evolving and expanding. In summary, this page offers a valuable resource for researchers seeking to explore and understand complex datasets across multiple disciplines. By providing access to comprehensive lists of relevant information, it facilitates collaboration, accelerates discovery, and ultimately contributes to the advancement of knowledge in various fields. In the realm of differential evolution, recent advancements have been pivotal in addressing constrained multi-objective optimization problems. The application of various mutation operators significantly influences the efficiency of the optimization process. A review of state-of-the-art works underscores the importance of differential evolution in solving complex engineering challenges. Moreover, the paper delves into the application of different optimization algorithms for parameter estimation in photovoltaic models. This includes the Jaya algorithm, Dandelion optimizer, Northern Goshawk optimization algorithm, and the comprehensive learning RAO-1 algorithm. Each algorithm's effectiveness in identifying accurate photovoltaic model parameters is discussed, along with their performance comparisons and potential limitations. The authors emphasize the need for further research to enhance the efficiency and accuracy of these optimization techniques, particularly in the context of renewable energy systems. They conclude by highlighting the significance of differential evolution and other optimization algorithms in tackling complex engineering challenges, especially those related to renewable energy and sustainability. The paper underscores the importance of continued research in this area to develop more efficient and effective optimization methods.